Hello, in this video we are going to talk about the rheology in fluid mechanics. We are going to see the different types of fluid, Newtonian and non-Newtonian fluids and their subcategories. So, first of all, let us know what is a rheology. So, let's see rheology. Let's see the definition of rheology. Well, it is a branch of science which deals with study of different type of fluids in the flow. It's a branch of science that deals with study of different types of fluids in a flow. Well, okay. Now we are going to see the categories of our fluids. So here I'm writing fluids, and now we are going to see its categories. The first one is Newtonian fluids. Well, as the name suggests, Newtonian fluids, that means they're going to obey Newton's law of viscosity. And second one is non-Newtonian fluids. They won't obey Newton's law of viscosity. What is Newton's law of viscosity? So here I plot a graph of shear stress versus rate of shear deformation, that is d theta by dt, or you can also say is du by dy. So their graph would look something like this. It's a straight line. That means that tau is directly proportional to d theta by dt. It implies that tau is directly proportional to du by dy. That means tau is equal to mu du by dy, where mu is constant of proportionality. Also mu is slope of curve. It's a constant. So this is Newtonian fluids. So let's see some examples of Newtonian fluids. It includes air, water, He, kerosene, petrol, etc. The second is non-Newtonian fluids. So I'll write it on a different page. Non-Newtonian fluids. They are categorized into two categories. First is time independent. Second is time dependent. Time independent is further categorized into three categories: pseudo plastic fluids and dilatant fluids. Bingham plastic fluids. And time dependent is categorized into two: thixotropic and rheopatic. Okay, so this is the category of non-Newtonian fluids. Before discussing non-Newtonian fluid, let us discuss some theory regarding it. Okay, shear is equation is something like this. A du by dy raised to power n plus b, where A is consistency index, n is flow behavior index. Okay, so we will see this equation again into the classification of non-Newtonian fluids. So first of all, let us discuss pseudoplastic fluids. These are also called as shear thinning fluids. Shear thinning fluids. Okay, so the equation looks like this. Okay, so we can also reframe the equation like this. So this is mu apparent. Here in the pseudoplastic fluids, we take value of n is less than 1 and b is 0, where n was flow behavior index. So what would the graph of pseudoplastic fluid look like? Let's see. It will look something like this. This is mu and this is du by dy. So we can see that as the strain deformation increases, the slope decreases. So if the slope is decreasing, that means the value of mu apparent is decreasing. Hence, we can say that these are shear thinning fluids. Okay, let's see some examples of pseudoplastic fluids, that is blood and milk. Okay, we have covered our first, that is pseudoplastic fluids. So let's demarcate it as covered. Now we'll be talking about dilatant fluids. So let's discuss about dilatant fluids. Well, dilatant fluids are, these are shear, okay, these are shear thickening fluids. Okay, and the pseudoplastic fluids were shear thinning, these are shear thickening. Here the value of flow behavior index is going to be greater than 1, whereas b is greater is equal to 0. The graph would look something like this. So we can see the value of slope is increasing, hence these are shear thickening fluids. Well, let's see some examples of dilatant fluids, that is concentrated solution of sugar, solution of sugar, and rice starch aqueous suspension. Let's frame the equation also, which will look like this. This is mu apparent. So we can see that the value of n here is going to be greater than 1. So this is going to be positive. Hence, as du by dy increases, the mu apparent is going to increase. So that's why these are shear thickening fluids. Dilatant fluids are shear thickening fluids. Okay, we are covered with dilatant fluids and pseudoplastic. Let's cover Bingham plastic fluids. Bingham plastic fluids, they are also known as ideal plastic fluids. So let's write, they are also called as ideal plastic fluids. Okay, let's use the demarcation. Okay, the equation would look something like this. The graph. Pardon? Yeah, this is the tau naught value, and this is generally tau and du by dy. Their equation is like this: a du by dy raised to power n plus b. Here the value of n is 1 and b is tau naught. Okay, it's also called as yield stress. The example is drilling mud toothpaste. Next, we are approaching towards time dependent fluids. They are categorized into two: thixotropic and rheopatic. Here, the mu apparent value changes with respect to time under a given shear rate. So, let's see the graph of thixotropic fluids. Graph would look something like this. I forgot to mention that they are also shear thinning fluids. As you can see from graph also, these are shear thinning fluids because the slope is decreasing as the strain is increasing. So here, this is again some yield stress we are observing, and this is du by dy, and this is tau. So here mu apparent decreases with respect to time under a given shear rate. An example is paint printer's ink. So the example of isotropic fluids are paint and printer's ink. Now we are coming towards rheopatic fluids. The graph is like this. So we can say that they are shear thickening fluids. Since the slope, we can see that slope is increasing at increased value of shear strain. So this was tau, this was du by dy, and this is tau naught yield stress. So the example here, mu apparent increases with respect to time under a given shear rate. The example is gypsum suspension in water. Gypsum suspension in water. Okay, so this was a major classification. Now we will look at some other fluids also, like say ideal fluid. Whom do we call ideal fluid? These are frictionless or inviscid fluids whose dynamic elasticity is equal to 0. Okay, so the value of mu is 0. Dynamic viscosity, pardon, I said it elasticity. So the dynamic viscosity is 0. These are ideal fluids. There are no surface tension effects. No surface tension effects. How would their graph look like? It would look like straight like this only, where this is tau and this is du by dy, or we can say d theta by dt also. Okay. Next is viscoelastic fluids. So viscoelastic fluids have property of elasticity only up to a certain limit. So let's write it. Property of elasticity up to certain limit. Example, biological fluids. Okay, so this much we have covered. Thank you for watching this video and subscribe to our channel. Once again, thank you.